recording here as well, and just answer the last question. The last question was uh, about the some task you'll get as part of the exam. As I explained, you will all get the same geometry of one practical problem. So I'll give you the geometry of practical problem, and I'll give you the the, the field test results about that problem. Maybe I can prepare it here just to have some free paper to draw. So we'll prepare something like this. I'll of course draw it in details. Let's say after maybe in 2 weeks, I'll define the geometry of this practical problems, the angle, slope angle, the details, the surcharge load. That is something like, or the some construction, the viaduct or bridge near the slope will define some additional load at the slope, and then I'll give you the information about field tests at the location. It can be SPT data, it can be CPT data, it can be some soil sample data, like some test results here, and I'll send you all this result and ask from you to predict the bearing capacity of this surcharge load. What's the bearing capacity of this soil profile with these in situ characteristics and with this geometry? So you'll be free to use any correlation for SPT to parameters, for CPT to parameters. You'll be free to use any software for solving this problem. You'll be free to use any empirical approach for predicting this result. So every one of you will have probably a different or more or less similar result. But that result will be defined according to the assumptions you will precisely define in your answers. Of course, I'll prepare this question or this test. I don't know how you can call him. I'll prepare it in details, defining the geometry, the input data, and what is expected from you, what to show, what results to get. And after you send those results, I'll collect it in one data and show the results to everyone, just to uh, just to indicate how important is it to use this correlation or this theory, what are the advantages of this theory, what are the disadvantages of one theory, and so on. So that will be your task, but as I said, I will define it in detail by one document that I will send you as a part of this exam. Okay. So time by time, I'll check this chat if you also write a question here. If not, as I said, you can always stop me and ask a question about what we are discussing. So this is actually a first topic about what we said at the introduction, is that we'll show the basic principle landslide mechanism. Will define why do we have landslides, where do we have landslides, in what conditions we have landslides, and similar problems regarding the nature of the soil. So the first question that needs to be clear is why the landslides occur. Why the landslide occur? Well, the landslides occur due to two main aspects. The first aspect is a nature, and the second aspect is a human factor. Of course, it is very often it is actually a combine. It's not only one or the other. It's usually a combination when you have some landslide prone area, and if it's combined with a human factor, there is some uncontrolled excavation or embankment construction, it can lead to a landslide occurs. When we are talking about Bosnia and Herzegovina, but I believe that a similar condition we have worldwide and in the neighborhood, there are some um, there are some landslide maps that are collected. They are collected in the one document, one large map that gives an indication of where the landslides can be located, are located, and so on. These maps are not so detailed, but they can definitely show that in the areas where the soil-like materials are more thick, these areas are more prone to sliding. So when you have some uh, rock rock mass areas, like I don't know, in the south part of Bosnia and Herzegovina, you expect not to have problems with the landslides, and so that globally you can get some indication of uh, how prone to sliding some area is. Where you have deep deep layers of soil, then the possibility of sliding is increased. We'll show some well-known landslides related to highway construction in these parts. So I'll give you then more information. But here on these photographs, you can see some landslide activated after the highway construction. You can see the highway construction. It's it's not under construction. It's already constructed highway, but up above you can see the landslide area activated. This is actually not a highway; it's a regional road, but a large landslide occurred near this area, and then a totally destructed regional road is shown here. This is interesting soil profile showing the mechanism of landslide sliding. This is a soil-like material, and this is a rock material. And really, if I have to define only one sliding mechanism, and I have to choose one most often sliding mechanism, it would definitely be a sliding of soil on the top of the rock surface. So the rock is relatively stiff, strong material that is not sliding, and this is relatively poor, low strength soil materials, and then the sliding usually occur at this contact, at this interface between the rock and the soil. What is most important, this rock material is usually impermeable, so the water cannot go down to this rock material. So the water then just collects here above the rock surface. And we have the water level increment, and as the water level increase, the safety factor of this slope is going down. We'll show the principles of the calculation, some main aspects of the water level influences the sliding. But when we are dealing with the landslide in Bosnia and Herzegovina, but I believe the similar conditions are not say worldwide, but definitely locally in this area, you will see that the most of the landslide are such a mechanisms that the soil-like material slides on the contact with the rock, and the main trigger that that uh, that brings some slope in the unstable condition is a water level, actually the increment of water level, of course with the combination of human factor, with some excavation and additional load at the slopes. As we said at the beginning, we have to separate two interaction of landslides and highways. The first interaction is that we are constructing highway in landslide areas. So we do it if we really have to do it. This is really not a good practice to put during the road planning to bring the highway in the landslide area. Of course, the landslide is not always a very big problem. The main indication uh, regarding the answer to the problem is some landslide a problem or not is the depth of the landslide. What does it mean? If this is the soil-like material and this is rock material that is not prone to sliding, very good stiff material, the main information about landslide is this. And this is the depth, the height of this soil-like material that is prone to sliding. So some failure surface would look like this. So this is moving soil mass that is unstable in natural conditions. So if we need to put our highway route through this area, then we better try to put it where this height is, let's say, lower than 5 meters or I don't know, 6 meters. But if it's above 10 meters, then we can really expect a lot of problems. If it's 15 meters, 20 meters, then we could have really a lot of problems to bring this condition into stable areas. Of course, everything had a technical solution. Every problem had a technical solution, but that technical solution really becomes so expensive, so complicated to construct. So it needs so much energy to solve that kind of problem, and you'll see that from some case study example. I show this picture here where this viaduct passes the landslide areas, and I don't know, 5 or 10 of these footings are passing the landslide that is 16-meter deep. Very, and you get an indication of what the foundation system must be like to support this huge load that is the result of the sliding of this very deep soil mass. Part B relates to the landslides activated due to highway construction. So, or like over here, we had in cross section we had one hill like this, and then the highway route is designed like this with some slopes, long-term slopes. And after the excavation of this, an instability occurred here, and all this part of the wall actually slide in this area. So this is typical landslide occurred after the highway construction. Of course, before the highway construction, no chances of any soil sliding could be possible because the hill looked like this and then went here. So from both sides, it's excavation like this. And then you have some measure that we didn't count for and that had to be performed here to enable the road traffic to perform here along this route. So we'll always discuss about this, and we'll discuss about principles of one and the other conditions of interaction, landslides, and highways. Maybe when we get some useful lessons, useful experience from failures, maybe these conditions could be reduced, and that's actually a main idea of learning these things of listening to lectures like this is to prevent this to happen. But it would also be good to prevent this scenario, especially if we have deep landslides. When the landslides are deeper than 10 meters, the construction of highways in that areas has a technical solution, but you need a lot of energy, a lot of money, a lot of work to do to construct a stable construction in these conditions. Regarding the unstable areas, we can also define two parts of instabilities. First one is unstable slope. Unstable slope is some slope that is at the verge of failure, that is actually at the limit of the equilibrium. It is in theory defined as safety factor of that slope is near to 1.0. So we have a slope that if we observe it, if we monitoring with some geodetic wrapper points, fixed point, or some inclinometer data, we'll probably have some displacements happening in some slow range, like, I don't know, 1 centimeter per year or 1 centimeter per month. That is something that is unstable, that is slowly moving soil mass. And that can be defined as an unstable slopes. Unfortunately, we have a lot of slopes at the verge of failure, but it's actually very often called a conventionally stable or potentially unstable slopes. These are the slopes that had a safety factor just above 1, but not a lot above 1, maybe in the range of 1.25 to 1. So if you observe the slopes like this, you probably won't measure any displacement. It is not moving, it is potentially stable. But when you perform some excavation, some additional load, and you do something with that slope, then it very, very easily becomes unstable slope with a safety factor of 1. So this is also something that very often occurs during the construction of highway. What it means? It means we have a slope like this. This is a rock material that is stable, not prone to sliding, and we define this sliding surface here with the safety factor of 1.2, let's say. So no displacement, the slope is not moving, it is potentially stable. But what we do then we excavate here an excavation to enable the pass of the highway. And what happens? It happened that we have failure like this, and all this mass slides here and cause a lot of problems. The cost increment and the dynamic plan of construction works increment and so on and so on. So we have to be very careful, not only with this, with designing the uh, slopes in the unstable, the road in the unstable slopes, but also in the areas that the safety factor of in situ conditions of the natural conditions is not far from 1.0, and that is so-called potentially unstable. So any construction we perform can bring it to unstable areas. That's why in this condition we have to define some supporting measures, some retaining walls, some anchor walls, and so on to support this excavation area and to increase the stability of this surface above the excavation. Here is the list of some natural triggers and human factor triggers that are listed here as very often more common than the natural triggers. But of course, we have some combination of these two factors always. The most important, most often natural triggers of the landslide is the surface and underground water that is caused by heavy rainfall and snow melting. We know that most of the landslide is activated during the heavy rainfall and slow melting, and it is the experience that tells us that the water level increment is a first factor that triggers the landslide to failure. Of course, the slope cannot fail if it has a very favorable engineering geological characteristics. So we always have some engineering geological conditions that makes that slope prone to sliding. So these two aspects are the most important two aspects for the landslide activated here at local areas. Of course, you can have some other aspects of natural triggers. The first one is a lowering of groundwater level in rivers and lakes. What that means if you have a slope like this and down there you have some river with this level, and let's say you have a soil material here and rock material here. Well, this can be some gravel and sand at the end of the river, and this can be some sandy clay up above, and this could be a unpermeable rock materials. So this river actually flows, and the water cannot seep down to this unpermeable material. What happens that the groundwater level inside the slope is usually similar to this level into the river. But when we have the increment of this water, then this water can come here. The increment in water level in the river means the increment in the water level in the soil above. And what happens when we have a lowering of this water level from this point to this point? Then we have that the water level in the river drops down, but the water level in the soil material cannot drop down immediately, especially if you have some clay material inside. So then you have the water level in slope like this. And that is actually a critical moment. Why? Because when we had this water level in the river here, it acts actually like a support for this slope. But now we removed that support, but still the water inside the slope remains at this high level. So that can be a critical part of the slope instability when the water in the river drops down suddenly. There are some more aspects that can cause the landslide to fail, like submersion of soil particles. That can be related to a shallow sliding 2 or 3 meters, where some holes can be formed inside the sandy clay material. We can also have a seismic activities that are not very often uh, here in local practice, and actually we don't have so much problems with landslide activated due to earthquakes like you have in, I don't know, some other countries in the world wide like Japan or and so on. Another indication of or uh, cause of landslide sliding can be a slope inclination. If you ask someone who is not familiar with the landslide related problems, he would probably say that the beginning, as the slope angle increases, the problem increases. So if you have one slope like here 45 degrees, and you have the other slope like here, I don't know, 15 degrees. This is, let's say, some this is option 1, this is option 2. And if you ask someone what could be more prone to sliding, option 1 or option 2, probably if you're not thinking and if you don't have some experience, you would probably choose 1. But actually it's not true. It's not true. The most landslide related problems occurred at relatively low angle slopes that range from 10 to 20 degrees, but not to this very steep slope. Because when you have a naturally steep slope, it is usually some rock-like material. It's usually a rock mass or something that is actually formed in a very steep slope naturally. But when you have a very kind of flat slope at 10 degrees, 15 degrees, 20 degrees, then you have to be very careful, especially if this soil-like material is deep, let's say more than 10 meters. Because when it's shallow, 2 meter, 3 meter, then it's not a big problem. You can excavate all that part, but bring some relatively small retaining wall above, and it will stop it from sliding. But when you have deep soil-like material on a relatively flat area with a small slope angle, then it can be a real problem. And most of the landslide related problems really occurred in the areas sloped about 10 to 15 degrees in the horizontal. So the slope angle is actually not a very important indication when you are thinking about instability problems. Actually, the higher the slope angle, the possibility of sliding in natural condition and landslide prone of that terrain is lower. Regarding the human factor, who the most often mistakes and the construction that causes the landslide are inappropriate cut slope excavation. So we are doing excavation with any support measures and uncontrolled dewatering of the area, cutting of the trees and vegetation removal can bring water deeper into the soil-like material. Generally, inappropriate earthwork performance. If you construct some embankment at the top of the unstable area or potentially unstable area, it can bring that area totally to unstable conditions. Additional human factors that can influence to increase the possibility of sliding are vibration induced by heavy machines at the slope, uncontrolled mining, or dynamic loads at the roads that can increase the possibility of sliding. But the most important human factor is often inappropriate earthworks and inappropriate cut slope excavation. That means if you have a slope like this and you do the excavation like this, of course you can cause a landslide sliding above. Or if you have a slope like this and then you bring here some embankment at the top of this hill, you can of course cause this downslide. There are so many failures observed like this that are performed due to additional load at the slope or that are caused by excavation without appropriate support with some support measure that will keep this uphill material stable. Of course, they are often combined with the inappropriate poor geological engineering characteristics of soil and due to heavy rainfall increase in water level into the soil. Now, now I'll show you some basic theoretical background in that is used in analyzing the landslide related problems and soil stability problems. I'll really show you some basic theoretical background, and I'm 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 sorry if I'll be too too if I'll show just too elementary knowledge, but I think it can be useful to show these elementary principles that are really used in solving very complicated and practical problems. What what can be used as elementary concept is actually the very simple principles from mechanics of materials, but you have some, let's say, wooden block laying at the concrete block, and then you increasing the slope of this concrete block, and at one moment, of course, you will you will have the slidings of this wooden block when the sliding occurs, but it occurs when this force T, there is a component of this force G becomes lower than this friction resistance. And friction resistance is actually a multiplying is the number get multiplied by this reaction equal to this component and to friction coefficient defined as F0 here. What happened at the soil? What happened at the soil is very similar conditions, but we don't have a friction coefficient since we have sliding of soil on the other soil. So we have sliding soil on soil, so then we use actually a parameter that is called internal friction angle, and we define it by internal friction angle marked as phi, but actually the tangents of this internal friction angle is nothing else than this friction coefficient used in this main principles of mechanics of sliding of two of one stiff body on the other. It can also be illustrated in this diagram that defines the component N force and T force. So we have N force and T force, and we have one limit. Limit, this red dotted line, that is defined by the slope of F0. For any combination of T and N that lays down below this line, we'll have that it will be defined in the physical problem as a stable. This wooden block will be stable. But when we get this combination of shear force and normal force that is on this dotted line, then it defines the condition of limit equilibrium when this block slides down. Finally, this condition of this green point is actually not possible, since already as long as we reach this combination, this sliding occurs and there's no possibility of additional increment of this shear load. A really similar condition occurred in the soil, but we don't have a friction coefficient. We have internal friction angle, plus we have the additional parameters, and that is the cohesion value. The cohesion value has the unit of stress, and it actually defines this measure. It defines actually the resistance to sliding without normal component. So when there is no normal component, when there is no force that pushes this body down perpendicular to this sliding surface. If you don't have this, if you don't have any resistance here, then you don't have cohesion. But soil actually have cohesion, and that can be modeled here in this simple physical model as if you use some glue. If you use some glue and you link this wooden block to this concrete block, then you'll have additional resistance to sliding. You'll need additional force to slide this, even if there is no normal force. So if this lay down horizontally and there is other block here and you stick it to this block, you'll have some resistance to the shear force. You won't be easy to slide it down to this surface, even when there is no normal force, since it's stick down by some glue to this surface. So that's what happens in the soil. You have clay material that is stick, the particles of clay are stick to each other, and then you have some resistance to sliding even without normal component of the stress. And that's exactly what it's doing when modeling, when trying to predict the future of some slope. When we are modeling, we are actually predicting the stability of some slope. We are predicting it and we define it with a safety factor. If we said the safety factor is high, 1.5, 1.2, then it means we are far from the failure condition. And that's what we want to reach. But if we predict that the stability of slope is defined by safety factor need to 1, that means we are next to this line. We are next to this line. The safety is just here where we don't want it to be. So any excavation, incremental water level can actually reduce that safety factor and cause sliding of the slope. So the answer to this is that this block will slide when the T-N ratio reaches red line. When the ratio of the T force and N force, and there are the components of this weight, reaches red line, we'll have sliding. This similar conditions, similar things happening in slopes, in the landslides, in the soil-like materials. How the only difference is that we don't have this slope is not defined by the friction coefficient, but it's defined by the internal friction angle. So this slope becomes tangent phi, not F0. And we often have this, that this line do not intersect the Tn system in the 0, but it intersected here. So we have this resistance without normal load, and that physically can be explained like the sticking together these two blocks. And that's exactly what happened in clays. We have particles stick together by these interaction forces called cohesion that is defined as this length. That is resistance without normal stress. Resistance without normal stress. And this tangent phi is actually an increment of resistance due to increment of the normal load. Okay, we'll be interrupted once again in 2 or 3 minutes. So I suggest you to ask some questions if you have any before I continue with the next class in 2 or 3 minutes. If there's no questions, I'll just stop this part and continue in a few 2 or 3 minutes.